Welcome to your severe weather analysis for Brisbane, Friday, December 12, 2025. This morning's 10 a.m. sounding reveals a complex atmospheric setup with modest instability near the surface. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Let's examine this morning's atmospheric profile. The standard Skew-T diagram shows temperature in red climbing from 24.5 degrees at the surface, while the dew point in green sits at 22.2 degrees, giving us a narrow 2.3 degree spread. This indicates abundant moisture near the ground. The blue dashed mixed layer parcel path shows only 163 joules per kilogram of CAPE, with a small pink shaded area between the parcel path and environment representing this limited fuel. There's essentially no blue shaded CIN, meaning no CAP is holding back convection. However, the storm mode is listed as sub-convective, meaning the surface parcel alone requires a trigger to initiate storms. The lifted condensation level sits at just 299 meters above ground, indicating very low cloud bases if storms develop. What's notable here is the surface-based parcel shows much stronger potential, with over 2400 joules per kilogram, but this energy is only accessible if surface air can be lifted. Now let's look at the enhanced multi-parcel comparison. This plot reveals the full complexity of today's setup. The pink-dashed most unstable parcel, originating from the surface, shows a large pink shaded CAPE area extending from the surface up to around 180 hectopascals, representing 2488 joules per kilogram of potential energy. Notice the small blue shaded area near the surface showing minimal CIN of essentially 0 joules per kilogram. The equilibrium level, marked with the yellow EL box, sits near 180 hectopascals at roughly 13 kilometers. Meanwhile, the blue dashed mixed layer parcel shows dramatically less CAPE. The green LCL box near 980 hectopascals marks where the most unstable parcel would condense. This comparison reveals Brisbane has significant energy available, but it's concentrated in the surface-based parcel. If storms can tap into this surface instability through strong convergence or lift, they could become intense. The transformation here shows why storm initiation is the critical question today. The hodograph reveals Brisbane's wind shear environment and storm motion characteristics. Winds near the surface blow from the east-northeast at around 6 meters per second, shown by the dark blue portion of the hodograph. As we climb through the lower atmosphere, winds veer through the southeast, then back toward the southwest in the mid-level shown by the green and yellow colored segments extending to the right. The 0 to 6 kilometer bulk wind shear measures 7.4 meters per second, which falls well below the 20 meters per second threshold needed for supercells. The bunker's right mover storm motion vector, marked by the red RM star in the lower left quadrant, points toward the south-southwest. This means if supercells were to develop, they would track toward the south-southwest. However, with such weak shear, supercells are unlikely. The 0 to 1 kilometer storm relative helicity of just 25 meters squared per second squared confirms minimal low-level rotation potential. The 0 to 3 kilometer SRH of 141 meters squared per second squared is moderate but insufficient without stronger CAPE. For emergency services, this wind profile indicates if storms develop, they would be disorganized pulse storms or weak multicells rather than organized severe thunderstorms. The low shear environment reduces the threat of widespread wind damage, though isolated microbursts remain possible given the moderate decape of 607 joules per kilogram. The atmospheric refractivity profile, or N profile, shows Brisbane's stability structure with height. The blue line represents the Brunt-Väisälä frequency, which measures atmospheric stability at each level. Near the surface, refractivity values around 350 N units indicate typical boundary layer conditions. The orange-shaded elevated duct layer between approximately 2,000–2,200 meters shows where temperature inversions or moisture gradients create anomalous radio wave propagation. This elevated duct coincides with the weak inversion detected in the sounding between 790 and 794 hectopascals. Above 6,000 meters, we see the yellow-shaded superrefraction zone where strong stability suppresses vertical motion. For severe weather assessment, the relatively smooth N profile through the mid-levels indicates no strong stable layers that would enhance downdraft potential. The moderate decape of 607 joules per kilogram combined with this stability structure suggests microbursts are possible but not highly probable. Emergency services should note that if storms do develop, the primary threat would be brief heavy rainfall and isolated wind gusts rather than widespread severe wind damage. The lack of pronounced dry layers in the mid-levels reduces dry microburst risk and associated fire ignition potential. Today's analysis shows Brisbane with limited severe weather potential. Modest surface-based instability exists, but storm initiation remains unlikely without strong forcing. Tomorrow shows even less favorable conditions with minimal CAPE forecast. Always consult the Bureau of Meteorology for official warnings and forecasts. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia.